this video, I would like to explain classification of elements and periodicity in properties, synopsis points under concept session. So, in this chapter, we are going to discuss about atomic number, which is denoted with Z, modern periodic law and periodic table. That means total description of periodic table about periods, groups. Next, trends in periodic properties. So, in a periodic properties, very important topic for competitive exams. So, in periodic properties, we'll discuss about atomic radius, ionic radius, ionization energy, electron gain enthalpy, electron negativity, next nature of oxides, diagonal relationship, and so on. We'll discuss points one by one. So, first subtopic is atomic number. Here, Moseley discovered atomic number of elements by taking X-ray spectra of elements. He has given two graphs. So, first between atomic weight and frequency root nu of elements versus atomic weight, and the second graph frequency versus atomic number. So, he has concluded that root nu versus atomic weight is irregular graph. That means so many points were missing from normal line, irregular graph. But between frequency and atomic number is regular graph. So, here root nu is frequency of X-rays emitted by different elements, and atomic weight, first graph. Next, root nu, frequency of X-rays emitted by different elements versus atomic number, second graph. Here there is regularity in case of atomic number. So, from this he has concluded the periodic property of elements is atomic number but not atomic weight. That means simply properties are directly proportional to, I will write here, properties of elements function of atomic number but not atomic weight. So, simply atomic number is the fundamental property of all the elements. So, first graph is irregular and the second graph is regular. So, clearly we can say graph between root nu, frequency, and atomic number is a straight line. This is the most important linear graph. So, root nu is frequency of X-rays emitted by different elements and Z is atomic number. And Moseley concluded that atomic number is the more fundamental property of elements. And he has given one relation root nu equal to A into Z minus B, where root nu is frequency of X-rays emitted by different elements, Z is atomic number, and AB constants which are same for all the elements. Which are same for all the elements. Very important. This is Moseley's relation, root nu equal to A into Z minus B. Modern periodic law and periodic table. So, modern periodic law was given by Moseley based on Moseley's relation, root nu equal to A into Z minus B. So according to Mosley, fundamental property of elements is atomic number but not atomic weight. So from this we can say physical and chemical properties of elements are periodic functions of their atomic numbers. That means simply we can say properties of elements are function of atomic numbers. So based on atomic number, we can predict the properties of different elements. That is main property here. So modern periodic law based on atomic numbers. That is Z. We can explain each and every property by taking atomic number as fundamental property. Next point. About modern periodic table. So it was designed by Niels Bohr by using electronic configuration. Bohr has given electronic configuration. So atomic number means nothing but electronic configuration. So modern periodic table is based on electronic configuration. Therefore, it will be also known as Bohr's table. So it contains 7 periods and 18 groups. This point is very important. In IUPAC system, 18 vertical columns. That means simply vertical columns are nothing but groups. 18 vertical columns are named as 1 to 18 numbers. So in IUPAC system, group numbers are 1 to 18 in a line. Next, this point is very important. Elements belonging to the same group have same number of valence electrons and their properties will be similar. That means elements falling in the same group will be having similar chemical properties. Similar configuration means similar property. Similar electronic configuration gives similar properties. We can explain properties based on valence electronic configuration. General electronic configuration of S-block elements. NS1 to 2. So we know NS1 means, I will write here, NS1 and NS2. NS1 means first A group alkali metals and NS2 2A group elements alkaline earth metals. Next, general electronic configuration of P block elements. NS2 NP1 to 6. Gradual filling of NP subshell. Next, general configuration of D block elements. N-1 D1 to 10 NS0 R1 R2. That means I will write here for D block N-1 D1 to 10 gradual filling and NS0 R1 R2. For some elements NS0 will be there. Simply for palladium. Palladium has NS0. NS0 configuration. No electrons in NS subshell. Some elements will be having NS1 configuration and some elements NS2. Like that. NS0 R1 R2. Next for F block. N-2 F1 to 14 gradual filling. N-1 D 0 R1. Some elements will be having n minus 1 d 0, some elements d1. And ns2 is common for all the elements. ns2 common. Next here, most important point is ns. What is ns? ns is valence shell or ultimate shell. n minus 1d penultimate shell. n minus 2 f is anti-penultimate shell. Remember these points. ns is valence shell, n minus 1d penultimate shell, and n minus 2f is anti-penultimate shell. So very, very important point. These shells are very, very important. Anti-penultimate. Next. Next here one more point is there. Last slide. Here elements having atomic number more than 92. That means after 92 are transuranic elements. Elements having atomic number more than 92 are transuranic. After uranium. Uranium atomic number 92. After uranium all the elements are transuranic elements or transuranium elements. Next. All transuranium elements are radioactive, synthetic and man-made or artificial. You can say artificial. Artificial elements. Next. The group containing most electropositive elements are group 1. Group 1 means, first A group. Most electropositive first A or group 1. Next, group containing most electronegative elements, group 17. Most electronegative elements are 7th A or group 17. So, group 1 is alkali metals. Group 17 halogens. Most electropositive first A or group 1, most electronegative 7th A or group 17 halogens. These two are important ones. Next, the group containing maximum number of gaseous elements, 0 group or 18th group, noble gas. Other names for group 18. Eighteenth group will be also known as 8A group or noble gases or inert gases or monoatomic gases or 0 group or aerogens. So all these are other names for group 18. Group 18 is also known as 8A group, noble gases, inert gases, monoatomic gases, zero group and aerogens, because these are isolated from air. Next. Here, group in which elements have zero valency or 18th group or zero group. We know that. That's why 18th group elements will be known as zero group elements due to zero valency. Valency 0 for 18th group due to completely filled subshells NS and NP. Octet configuration. Next. Number of gaseous elements in periodic table 12. This is also important. Number of gaseous elements 12. Hydrogen, nitrogen, oxygen, chlorine and noble gases. Next. This is also very important. Third B group is called longest group containing 32 elements. Third B or third group has 32 elements. How 13 means? Already we have 4 elements: scandium, yttrium, lanthanum, actinium. Next, 14 lanthanoids and 14 actinides. Total 32. Longest group is third B due to 30 elements. 4 normal elements, 14 lanthanoids, 14 actinoids. Lanthanoids and actinoids are present in third B group only. Therefore, longest group. Now, longest periods are 6th and 7th. Longest periods 6th and 7th. Longest group third B. Next, number of liquid elements: cesium, francium, gallium, mercury, bromine and UUB, that is 112, atomic number 112. Bm. Next, the S and P block elements except 18th group or 0 group are commonly known as representative elements or normal elements. Representative elements or normal elements. So total S and P block elements except noble gases. Noble gases are 0 group or 18th group are known as representative or normal elements. Next points. So already we have discussed this point. 0 group or 18th group elements are also known as inert gases. Inert means stable. They cannot form bonds easily due to completely filled shells. NS and NP subshells are completely filled. Next, all D block elements are transition elements except zinc, cadmium, mercury. That is, zinc, cadmium, mercury belong to second B. So, except second B elements, remaining all D block elements are transition elements. Next, all F block elements are known as inner transition elements. These are part of transition elements. Next, group 16, chalcogens. Chalcogens means ore forming elements. So I will write here. Chalcogens, ore forming. So most of the ores and the minerals contain these elements only. Chalcogens. Next, what are halogens? 17th group elements are known as halogens. Sea salt formers. So sea salts contain these salts only. That means these anions: fluorides, chlorides, bromides, iodides. Salts of sea contain these elements. Next, here one more point. In F block, we will be having two series of elements: lanthanoids, actinoids. Lanthanoids are also known as 4F series. Actinoids 5F series. Similarly, in D block, we have different series: 3D series, 4D series, 5D series, and 6D series. Have 4 series. Remember here F block and D block. In D block, 4 series of elements. F block 2 series, 4F series, 5F series based on the differentiating electron enters. Next one. This is the main topic of periodic table. Trends in periodic properties. So atomic radius increases down the group, and decreases along the period. So here group means, remember, top to bottom like that. Period, left to right. Group means top to bottom, period, left to right. So atomic radius increases down the group. That means top to bottom atomic radius increases. Next, across a period means left to right atomic radius decreases. So in atomic radius, we have 3 types based on type of bonded atom: covalent radius, metallic or crystal radius, van der Waals radius. Atomic radius is classified into 3 categories based on the type of bonded atom: covalent, metallic or crystal, van der Waals. So size order or covalent. Covalent radius less than metallic radius or crystal radius, which is less than van der Waals radius. So van der Waals radius is highest radius. Next. In case of anions, size depends on charge. In case of anions, charge depends on, that means size depends on charge. As the negative charge increases, size also increases. As the positive charge increases, size decreases. So these points, these total points based on these two points only. For anions, you have to compare negative charge. More is the negative charge, more will be the size. In next point, in case of cations, here anions, negative charge, cations, positive charge. Next, for atoms, that means for neutral atoms, that depends on Z effective. effective nuclear charge. As the effective nuclear charge increases, size decreases. Remember these 3 points. Here different orders are given. Fe, Fe2 plus, Fe3 plus. So order, as the positive charge increases, size decreases. Here also same. Mn, Mn2 plus, 3 plus, 4 plus, 5 plus, 6 plus, 7 plus. Positive charge gradual increase, therefore size decreases. Like that we can compare. Next here, cation is smaller than parent atom, but anion is larger than parent atom. Simply you can write like this. Suppose anion, next neutral atom, next cation. Anion size will be more than that of parent atom, that means neutral atom, and cation size is less than that of neutral atom. Size order. Very, very important. In case of anions, electrons will be dominating. Electrons more than that of protons. In neutral atom, electrons equal to protons. In cations, protons will be dominating. If electrons greater than protons, size increases. If protons greater than number of electrons, size decreases. Remember like this. Next, most important, in case of isoelectronic species, that means atoms or ions having same number of electrons, cations with greater positive charge will have smaller radius, with negative charge will have large radius. With greater positive charge, smaller radius, with negative charge, larger radius. So this is the point only. If electrons are dominating, size increases. If protons are dominating over electrons, size decreases. Or simply you can say, in case of isoelectronic species, isoelectronic, as the atomic number increases, size decreases. In case of isoelectronic species, as the atomic number increases, size decreases. Next. Here, steady decrease in atomic radius of lanthanoids from left to right with increase in atomic number is known as lanthanoid contraction. So, lanthanoid contraction is observed in case of lanthanoid elements from left to right. That is due to poor shielding effect of poor shielding effect of 4f orbitals. Lanthanoid contraction is due to poor shielding effect of 4f orbitals or 4f subshell. So in the lanthanoids, from left to right, atomic radius decreases gradually. That is contraction. That contraction is due to poor shielding effect of 4f orbitals. Next, ionization energy. The minimum amount of energy required to remove electron from isolated gaseous atom is ionization energy. So here M gaseous, that is neutral atom, that will be converted to unipositive. That is simply we can say IE1 is removal of first electron, IE2 is removal of second electron, IE3 is removal of third electron, and so on. So IE1 can convert neutral atom to unipositive, IE2 can convert unipositive to dipositive. So here it is the relation between different types of ionization energy. IE1 removal of first electron, IE2 removal of second electron, IE3 removal of third electron. So always this will be the order. I3 greater than I2, I2 greater than I1. So due to increase of Z effect. Ionization energy directly proportional to Z effect, effective nuclear charge. The force of attraction between nucleus and valence electron increases, ionization increases. Next. Here factors affecting ionization energy, atomic radius, ionization energy inversely proportional to atomic radius. Next, this point is very important. Ionization energy depends on charge. So as the positive charge increases, ionization energy increases. As the negative charge increases, ionization energy decreases. So here ionization energy is more for Fe3 plus due to more amount of positive charge. This will be the order. As the positive charge increases, size decreases. As the size decreases, ionization increases. So ionization energy also depends on electronic configuration. Elements with half-filled or completely filled configuration shows more stability and require more amount of energy to remove that electron, valence electron. So nitrogen and oxygen. So nitrogen will be having half-filled configuration. Therefore, it will be having more ionization energy when compared to oxygen. Next, in a group from top to bottom, ionization energy decreases due to increase of size. In period from left to right, it increases due to increase of effective nuclear charge. So in case of second period elements, this will be the order. Here abnormal pair is beryllium and boron and oxygen nitrogen. So beryllium greater than boron and nitrogen greater than oxygen. So in beryllium completely filled configuration is present. In nitrogen half filled configuration is present. Therefore, these two are anomalous pairs. Next in third period, aluminium magnesium anomalous pair. Sulfur phosphorus one anomalous pair. Similar. Magnesium has more ionization when compared to aluminium and phosphorus more than sulfur. So magnesium completely filled configuration, phosphorus half filled configuration. Remember these four pairs in second period and third period elements. Next, electron gain enthalpy or electron affinity. So enthalpy change when an isolated gaseous atom of element accepts an electron to form monogaseous ion is known as electron gain enthalpy. So electron gain enthalpy means the amount of energy released when an extra electron is added to isolated gaseous neutral atom to form uni-negative ion. Next, EA1 is first electron affinity. First electron affinity is always exothermic. That means release of energy. So electron gain enthalpy 1 or first electron affinity is negative for most of the elements. Next, EA2 or Second electron gain enthalpy is positive for all the elements. Second electron gain enthalpy is always positive due to inter-electronic repulsions. Inter-electronic repulsion. For most of the elements, first electron gain enthalpy is negative. That means by the addition of extra electron, amount of energy will be released. Exo and endo. Next, this point is very important. Large negative value of electron gain enthalpy reflects greater tendency of an atom to accept electron. So, more is the negative value, more will be the acceptance of extra electron. That means I will write point here. More negative electron gain enthalpy means more electron affinity. That means that atom will take up electron easily. Next point. Factors affecting electron affinity or electron gain enthalpy. It is also depends on size. As the size increases, electron affinity decreases. Next, one more important point. Electron affinity for completely filled or half filled orbitals will be very less or 0. That means the atoms having completely filled or half filled configurations will not take up electrons easily due to stable configuration. In that process, energy will be absorbed. That means endothermic. Electron gain enthalpy will be positive. So, different orders are given here. Electron gain enthalpy. You have to remember these orders. So, in this very important is halogens, 7th A group and the 6th A group. These two are very important. Repeating questions. 6th A group and here 7th A group. Chalcogens and halogens. Sulfur highest, oxygen least in 6th A. Next, chlorine highest. So, among all the elements in periodic table, chlorine has highest electron affinity. Highest electron affinity element is chlorine in total periodic table. Next, electronegativity is the tendency of an atom to attract the shared pair or bond pair of electrons towards itself. Simply, electron affinity is the property of isolated atom. Electronegativity is the property of bonded atom. Very important. In case of chemical bonds only, we can study electronegativity. That is the power of atom to attract shared pair or bond pair of electrons towards itself. Bond pair. Next. In a period, electronegativity increases. In a group, electronegativity decreases. Next, this point one, non-metallic elements have strong tendency to gain electrons. Non-metals can form anions. Metals can form cations. Metals can form cations. Non-metals can form anions. So bimetals are forming cations means electropositivity. Non-metals forming anions means electronegativity. Non-metals are more electronegative, metals are more electropositive. Therefore, they are forming cations. Metals, cations, non-metals, anions. In a period, non-metallic nature increases with increase in electronegativity. So, from left to right, electronegativity increases. Therefore, non-metallic nature increases. In a group, non-metallic nature decreases due to decrease in electronegativity. Metallic nature directly proportional to, right here, metallic nature directly proportional to electropositivity. Non-metallic nature directly proportional to electronegativity. If electropositivity increases, loss of electrons increases, metallic nature increases. If electronegativity increases, gaining of electrons increases, non-metallic nature increases. Therefore, metallic elements due to loss of electrons, they are forming cations. Next, non-metallic elements due to gaining of electrons, they can form anions. Next, factors affecting electronegativity. So, this is also very important topic. Electronegativity also based on atomic size. So, fluorine is the highest electronegative element in total periodic table. On Pauling scale, fluorine highest electronegative element in total periodic table. Value is on Pauling scale value is 4, which is highest. Second highest is oxygen 3.5. Next, one more point. Bond energy directly proportional to electronegativity difference between bonded atoms, and that is directly depends on stability. Bond energy or bond strength, we can say. Bond energy directly proportional difference of electronegativity between two bonded atoms, that is proportional to stability. Next, non-metallic oxides are acidic in nature. Metallic oxides are basic in nature. These two are repeating points in competitive exams. Non-metallic oxides are acidic. Metallic oxides are basic. Next, in a period from left to right, acidic nature of oxides increases. Left to right, acidic nature increases. Group top to bottom, basic nature of oxides increases. Means I will write here. Remember like this. In this direction, basic nature, top to bottom. In this direction, acidic nature. Left to right, acidic nature of oxides increases. Top to bottom, basic nature of oxides increases. Here some orders are given here. Basic nature in case of first alkali metals, lithium, sodium, potassium, rubidium, cesium. Down the group, basic nature increases. Next, alkaline earth metals, MgO, CaO, SrO, BaO. Down the group, basic nature increases. Next, acidic strength of oxides depends on electronegativity of central atom. If electronegativity of central atom increases, acidic strength of that oxo acid increases. Here we can compare either oxide or oxy acid with electronegativity of central atom. If electronegativity of central atom increases, acidic strength of that oxide or oxy acid increases. See here, order HNO3, H2CO3, H3BO3. So boron to carbon, carbon to nitrogen, electronegativity increases central atom. Therefore, acidic strength increases. Here also, from iodine to bromine, bromine to chlorine, electronegativity of central atom increases. Therefore, acidic strength increases. Next, acidic nature directly proportional to oxidation state also. Here HClO4 plus 7 oxidation state, HClO3 plus 5, HClO2 plus 3, HClO plus 1. So as the oxidation state of central atom increases, acidic strength increases. This is the order. Similarly, H2SO4 sulfur plus 6 oxidation state, H2SO3 plus 4 oxidation state. Therefore, H2SO4 more acidic than H2SO3. Similarly, here also SO3 plus 6 oxidation state, here plus 4 oxidation state. Acidic order. Next, one more point. Bond polarity. Polarity means difference of electronegativity. So, as the difference of electronegativity increases, acidic strength increases. Amphoteric oxides. What are amphoteric oxides? That means oxides having both acidic and basic properties are amphoteric. So, amphoteric oxides will be formed by beryllium, aluminium, zinc, tin, lead. Zinc, tin, lead can form amphoteric oxides. Important point. Oxides of beryllium, aluminium, zinc, tin, lead are amphoteric. So here remember this point also, bond polarity, that means charge. Charge depends on electronegativity difference. Next. The amphoteric oxides, beryllium oxide, aluminium oxide, zinc oxide, tin oxide, lead oxide, all these are amphoteric. So amphoteric oxides are the oxides having both acidic and basic properties. Therefore, they can react with acids as well as bases. Next, this is also very important. Neutral oxides. Neither acidic nor basic. CO, carbon monoxide, NO, nitric oxide, N2O, nitrous oxide are neutral oxides. NO, nitric oxide, N2O, nitrous oxide or laughing gas. CONO, carbon monoxide. These they are neutral oxides. Next point. Metallic character increases down the group and non-metallic nature decreases. Metallic nature down the group increases, non-metallic nature left to right increases. This is also important. Maximum covalency of first member of each group is maximum 4. maximum covalency of first member of each group, first element of any group is 4 due to only 4 orbitals. 2s means 1 orbital, 2p 3 orbitals. So due to the presence of 4 orbitals in valence shell, the maximum covalency of first element of each group is 4. Next, second member will be having d orbitals. Therefore, covalency will be more than 4. Whether it may be 5 or 6. So due to the presence of d orbitals in second member of any group, they can expand their valency to either 5 or 6. So first element of any group possesses maximum covalency 4. Second element possesses valency more than 4, that is 5 or 6. Next, first member of any group, first member of each group of p block elements have greater tendency to form multiple bonds, p pi multiple bonds. First member of each group of p block elements, that means 30 into 17. 30 into 17 groups can form multiple bonds, p pi. So like this, C double bond C, C triple bond C, C double bond O, C triple bond and like that. Next, reducing nature of elements increases down the group, oxidizing nature decreases. Remember like this. In this direction, reducing nature. So in this direction, oxidizing nature. In group from top to bottom, reducing nature of element increases. Left to right in a period, oxidizing nature increases due to increase of size. Okay, next. Very important property. The similarity in properties of elements in a group of second period and the elements present in next group of third period is known as diagonal relationship. See here, I am writing second period, lithium, beryllium, boron, carbon. Third period, sodium, magnesium, aluminum and silicon. So observe here, lithium and magnesium are diagonally similar. Beryllium, aluminum diagonally similar. Boron, silicon diagonally similar. So first element of second period diagonally related with the element of second element of third period, which is placed in next higher group. This is first A group, second A, third A and fourth A. So first element of second period diagonally related to second element of third period, which is placed in higher period, that means higher group. So first A lithium element is diagonally related to second A of magnesium, which is placed in next higher group. So diagonal relationship is due to the following reasons: similar size, similar electronegativity, similar polarizing power. So due to these three reasons, elements will be exhibiting diagonal relationship. So polarizing power means ionic charge by ionic radius square. So diagonal elements will be having these three properties. That means simply lithium and magnesium will be having similar size, similar negativity, similar polarizing power. Next, oxides of both, see here properties. Oxides of both beryllium and aluminum are important. That is similarity in properties. So lithium and magnesium can react with N2. Similarity. Next, oxides of both B and Si are acidic. Like this. So due to these three reasons, properties will be similar for diagonal elements. So this is the end of chapter. So periodic table synopsis completed. In next video, we'll explain one more topic. Thank you.